Hello, in this video I'll talk about aperture groups and why they are important for the pollination LEED tailored option 1 recipe. Aperture grouping is important because LEED tailored option 1 requires grouping of apertures. During the post-processing of the recipe, the dynamic blind schedule of each aperture group is calculated automatically by using the 2% rule. What happens when we add aperture groups is that we tell the recipe to do ray tracing for each group individually. This means that we can get the daylight contribution for each group and we can apply dynamic shading schedules on each group individually. For this reason, the groups must be room-based, which means that a group cannot span across multiple rooms. In the LEED Daylight Option 1 recipe, the dynamic shading schedules are calculated using the 2% rule on the basis of the created aperture groups. The 2% rule states that for each hour, the maximum floor area receiving direct illuminance of 1000 lux or more cannot exceed 2%. This means that for each hour of the analysis, the illuminance values are calculated for all shading combinations in each room, and the shading combination, which gives us the highest percentage, is selected given that it does not exceed 2%. When grouping apertures, you can follow a few criteria. One of the most obvious ones is the orientation. We want to group apertures facing the same direction, so we do not want an east-facing aperture grouped with a south-facing aperture. This is the case for room 2 here, where we have one east-facing aperture and two south-facing apertures. Here we would have to group this one on its own and create at least one group for these two apertures. Another thing you can look at is the shading pattern on the apertures. How are the context, for example, surrounding buildings, affecting the shading pattern on each aperture? If a number of apertures are facing the same direction but having different shading patterns, we might want to split those apertures into two or more groups, even though they all have the same orientation. Another option might be to group based on a control system in a building. Now let's take a look at how you can group apertures. Here I have a honeybee model, and all the light blue surfaces are just normal apertures. There are no aperture groups set up in this model. In Grasshopper, you can set up the aperture groups in two different ways. One is the manual way, where you need to use the dynamic aperture group component and add all the apertures that you want in this group. Here I have room 2 east, which is just this aperture in its own group. And then I have these two apertures in room 2 south here. I could further subdivide this south-facing group into two different groups, one upper group and one lower group. Later I will show how the results can change if I do that, if I in fact subdivide this group into an upper and lower group. So to do it manually, you'd have to repeat this process for all rooms that you want to simulate. And as one can imagine, this is a very time-consuming task for larger models, which is why we also added an automated option. Now let's see how the automated option works. First, let me visualize the aperture groups by the dynamic group identifier. So let me just disable this preview and this. What we have here is the dynamic group identifier visualized. And to group them automatically, I can use this automatic aperture group Grasshopper component under the Honeybee Radiance tab. First, I'll just show the default behavior. So I add the model, and set run to true. And now if I connect the model to the visualization, we should see all the aperture groups. Sorry, all the aperture being grouped. This is all the apertures that have an outdoors boundary condition. If we just take a look at room 2 again, we can see that it's created these two aperture groups. And here we have two aperture groups, which means that we have 4 different shading combinations, because each aperture group can be either unshaded or shaded. If we go back to the automatic aperture group component, we can take a look at the other options. As mentioned earlier, for LEED daylight option 1, the groups must be created on a room basis, which means that groups cannot span across multiple rooms. This room-based option is set to true by default, but let's just see what happens if we set it to false. Now we can see we have 5 different aperture groups. This is because we have 5 different orientations. And this leads me to the next option, which is how the apertures are grouped. By default, they're grouped by the orientation. If you want to use this view factor method, you can set this to true. By default, it's false, so it uses the orientation. If we set it to true, it will run a radiance-based script that will calculate the view factors for each aperture to the discretized sky. These view factors are then compared across apertures to evaluate if they can be grouped. And when using the view factor approach, the context and the surrounding buildings are very important, as they will affect the view factor values from aperture to sky patches. In some cases, you'll get the same grouping as you do with the orientation, and in other cases, if there is a lot of context, you will see that there will be that the groups will be subdivided into a larger number of groups. This size option is only used if view factor is set to true. The apertures are subdivided based on the size to create a grid for each aperture, and the grid is then used when calculating the view factor for each aperture. And here a smaller size will increase the accuracy of the view factor calculation. We also have this vertical tolerance option, and this can be used to define the maximum vertical distance allowed between any two apertures in a group. The distance is measured between the center points of the apertures, and if we set the vertical tolerance to 1 and go back to room 2, we can now see that it actually did split this group into 2, one upper and one lower group. That's because the distance from this center point to this center point in the vertical direction is larger than 1 meter. As mentioned earlier, I would show how splitting this group can actually change the results quite substantially. I have already run 2 simulations, one for each case, one where the south-facing group is one where there is only one south-facing group, and one where there are 2 groups. If we look at the case with just one group, which is what we have here, we can see that the spatial daylight autonomy is 38%. I did this simulation only for this room, only for room 2. But if we actually split the groups, or split the group into 2 groups, the SDA is suddenly increased to 64%. The reason for this is that when we have just one group, everything will be shaded when the 2% rule tells us that shading is needed. However, if we split the groups, there will be some hours where only one of the groups is shaded and the other group is unshaded. And here I have visualized the shading schedules for the 2 simulations. On the left, we have the case where the south-facing apertures are grouped into one. So what we want to look at here is the second dynamic schedule of the left column. The first schedule is for the east-facing aperture group, and the same for this column over here. We can see that there are some hours where both south-facing groups are shaded. If we look over here, for example, the hours around noon here, right? But we can also clearly see that there are a lot of hours where this group is suddenly not shaded. This is very clear by looking at the afternoon hours, where we can see that it is actually mostly unshaded. This means that we get a lot more daylight contributing to the spatial daylight autonomy calculation by splitting groups. For example, in this case, splitting a group in a lower and upper group. This was a introduction to the aperture grouping and the shading, dynamic shading schedules of the LEED Daylight Option 1 recipe. If you have any questions, please post them on the Pollination forum. Thank you for watching this video.